Every time you flip a light switch, a power plant somewhere has to spin slightly faster to provide that energy. The entire electrical grid operates in a state of continuous, delicate balance, constantly making microscopic adjustments to keep the power flowing. Grid operators easily manage these tiny, everyday fluctuations. They even have planned contingencies for single, large disruptions, like a major power station tripping offline. The real threat is a correlated event, multiple overlapping failures happening so quickly that the system cannot recover. On August 9, 2019, a severe thunderstorm rolled across Great Britain. A single lightning bolt struck an overhead transmission line near Cambridge. That strike created an immediate short circuit, pulling massive amounts of current toward the fault and causing a system-wide voltage dip across the network. Large power stations are designed to ride through these brief voltage drops, but in this case, two independent major generators failed to do so. In less than a second, both facilities automatically disconnected from the grid. At the exact same time, the sudden shift in voltage confused thousands of smaller systems. Protective software on distributed wind farms and solar panels misinterpreted the network fluctuation as a complete loss of grid connection. Working exactly as programmed, these systems intentionally severed their ties, taking even more power offline. A routine weather event initiated a software cascade. In a matter of milliseconds, a standard physical fault stripped nearly 2 gigawatts of power off the network, threatening the stability of the entire network. To understand why this is dangerous, you have to look at the macro physics of the grid. The core rule is simple. The in-feed, or power supply, must perfectly match E-outfeed, or power demand. On August 9th, a massive chunk of supply abruptly vanished, and that balance violently tipped. When demand exceeds supply, the grid's baseline heartbeat, its frequency, starts to drop. Engineers measure how fast this happens using a metric called the rate of change of frequency, or ROCOF. With 2 gigawatts gone, the British grid's frequency plunged. The system normally operates at exactly 50 Hz. The statutory limit for safety is 49.5 Hz. Once the frequency crosses that line, the network enters a state of severe instability where equipment can physically tear itself apart. A total frequency collapse is the ultimate failure. Italy experienced this in 2003 when cascading faults took down their national grid in seconds. When a grid goes black, you can't just flip a switch to bring it back. Operators have to perform a black start, a complex manual process of restarting individual power stations entirely from scratch, without help from the main network. It is a slow, grueling engineering challenge. In a world that runs on electricity, a frequency collapse means a total societal shutdown that can take days to fully reverse. To prevent a full collapse, the grid relies on an automated last resort defense mechanism called Low Frequency Demand Disconnection, or LFDD. This system is completely out of human hands. If the grid's frequency hits a critical absolute threshold of 48.8 Hz, automated relays instantly take over. Because the grid cannot conjure new power plants to replace the broken supply, LFDD solves the equation by forcibly reducing demand. It deliberately severs power to large segments of the public. The grid is explicitly engineered to amputate a limb. It will intentionally plunge neighborhoods into darkness as the only mathematical way to keep the wider network alive. Avoiding that worst-case scenario means operators have to act preemptively. Long before a store ever forms, they calculate the probability of a fault and purchase defenses to cushion the grid against it. This chart illustrates balancing financial and physical risks. The vertical axis is event impact, the horizontal is probability. Operators spend millions buying backup power to push potential failures across this boundary line, out of the red zone and into the green area of acceptable risk. Historically, the most reliable way to buy that security was through system inertia. This is the natural byproduct of heavy, spinning, synchronous machines, like the massive turbines inside nuclear and gas-fired power plants. The kinetic energy stored in all that rotating steel acts as a physical shock absorber. If a power plant trips offline, the heavy metal keeps spinning on momentum alone, naturally resisting any sudden drop in grid frequency without needing a single line of code or software intervention. Heavy, spinning metal has been our built-in insurance policy against blackouts for a century. But as we transition away from fossil fuels, those massive turbines are being taken offline. Modern renewable energy sources, like wind farms and solar panels, are entirely inverter-based. They supply electricity using power electronics, which means they do not have heavy physical rotors. As we add more renewables, we remove the grid's physical shock absorbers. The modern cure for an inertialess grid is a service called dynamic containment. Operators now rely on vast installations of grid-scale batteries. These battery banks use digital controllers to constantly monitor the grid's frequency. The moment they detect a drop, they blast enormous amounts of stored power into the network in a fraction of a second. They artificially mimic the stabilizing effects of traditional inertia. As the electrical grid goes green, keeping the lights on means relying less on the brute physics of heavy metal. We are now almost entirely dependent on split-second digital software to outrun the domino effect of a total collapse.